Hey class, this lecture is going to be on electric charge, forces, and fields, very similar to gravitational mass, forces, and fields. And we're going to be able to explain and solve problems related to electric fields and forces from Unit 3, Objective 2. We are looking at topic 5.1, which is kind of the movement of electric charge. And we're going to be able to state and use Coulombs' law to solve for electric forces between two charges. We're going to be able to mathematically relate electric forces and fields by using the definition of electric field strength. Hey, you're seeing words that we've seen before, right? Force, field strength. We're going to solve electric field strength. We're not going to draw electric field lines yet, because that's going to come up next week when we interact with both electric and gravitational fields. And we're going to be able to use superposition to determine the resultant electric force or electric field strength due to two charges. So, I mean, we're starting to see some similar words, right? Fields, forces, field strength, superposition. So we're really just applying the same process, but with new variables. And there's going to be a lot of new definitions, variables kind of being thrown at you. So, but to kind of help the comfort level, you'll notice that the equations that we're dealing with look familiar. We have an F equals KQQ over R squared, which is similar to F is equal to GMM over R squared. And we have an E is equal to F over Q, which is similar to G is equal to F over M. And then this one looks new. It is new, and we'll refer to it later. Recognize that we are looking at subtopic 5.1. So gravity, right? Gravitational fields and forces. We're in 6.2, but this one we're in 5.1. Okay, so just take a note of that. All right, let's start with a warm-up problem. We have the radius of a hydrogen atom is 5.29 times 10 to the negative 11th meters, as shown on the left. It's composed of a proton and an electron. But in our data booklet, we recognize that we have masses for a proton and an electron. So let's calculate the gravitational force acting between the proton and the electron. So I'm doing this because we know how to do gravitational forces, and electric forces and electric fields are coming up, in which we want to compare the two and see what's different about them. So I have the two masses. I know my gravitational force is equal to GMM over R squared. So I have 6.67 times 10 to the negative 11th times capital M, which doesn't matter which one I use. I'll use the electron, 9.11 times 10 to the negative 31st times 1.673 times 10 to the negative 27th divided by, and then the radius, which is 5.29 times 10 to the negative 11th meters. So I have 5.29 times 10 to the negative 11th meters, and that gets squared. So go ahead, plug this into your calculator and see what you get. I'm going to pause the video so I don't waste any time. All right, if you plugged it in, you should get 3.63 times 10 to the negative 47th newtons, and a big focus on that negative 47. This is super small. Super small force. Now I know they have very small mass, so maybe that's all you need, but to be honest, we're going to look at why this force is negligible compared to the electric force by a large quantity. Before we do that, we know we're looking at charges, we know we're looking at protons, we're looking at electrons. I want to take a pause right here and show how these forces occur with charges. So I'm going to open up a PhET in a minute. This is a PhET that interacts with electrostatic forces. That is forces between charges, between protons and electrons. Protons which are inside the nucleus, electrons which are kind of orbiting around the proton, and then neutrons are neutral, so they have no charge, so they won't be included in this. So I'm going to be moving this balloon around. I want you to be thinking about what could be happening, why are there forces that are occurring. Note there is also a support document for this that you will receive as well. So if I move it around and I get it close to the balloon, or I'm sorry, close to the wall, there are no forces interacting between the wall and the balloon. But if I go to the sweater, well, one, I don't see any forces, but I can rub the balloon on the sweater, and then I'm going to see what is going to happen when I let this go. Ah, it gets attracted towards the sweater. So there must be a difference in charge somewhere. And maybe if I get close to the wall, nope, still goes to the sweater. But maybe if I get close enough to the wall, goes to the wall. So that's interesting. So we definitely know there's a relationship between force and distance. And we also know there must be a relationship between charges. Now let me show the charges and see what's happening. Let's reset first and then show all the charges. So in the beginning, the balloon is neutrally charged, meaning for every positive proton, there's a negative electron, and that makes it neutral. Everything is neutral right now, but if I take the balloon and I rub it on my sweater, I'm going to pick up electrons. We can only pick up electrons because protons are part of the atomic nucleus. They cannot move between atoms. They are the atom, and the electrons are what's transferring between atoms and creating a difference in charge, and therefore creating this electrostatic force or electric force. And so when I put it in the middle, you can see that the attraction is between the negative charges in the balloon and the positive charges on the sweater. And obviously you see that the positive charges there's more of them in this in the sweater, and of course more negative charges in the balloon. But if I get it close enough to the wall, I can get it to where it goes to the wall, because the negative charges in the balloon are going to repel the negative charges on the wall enough to where the positive charges, which is what the wall is made of, as the wall is made up of atoms, which are made up of a nucleus with protons and neutrons, they get attracted to that. But what we're really looking at is a difference in charge. Why is there an attraction between negatives and positives, and what is that attraction actually looking like? So I'm going to open up a different PhET, one that may look fairly similar to the one that we did in the gravitational forces day. First, we're going to look at how charges affect the force. So if I move my charge 1 to a negative charge or to a positive charge, you'll notice that I have zero force acting on both charges when I have zero charge on charge 2. But as soon as I move one of those charges up to a positive or a negative, you can see how they start attracting or repelling. So let's start with both being like positive 1, or actually do positive 5 so we can actually see the direction of the forces. So when they both have positive 5, you'll notice that the forces are repelling each other, or the charge is repelling each other, and the forces are acting away from each other. That has to do with the two positive charges and the positive charges repelling. If I change this, now recognize the number, 3.61 times 10 to the negative 6th. If I move this to negative 5, I still get 3.61 times 10 to the negative 6th, but they are now attracting towards each other because I have a positive red charge and a negative blue charge, and positives and negatives attract. Similarly, if I move my red charge to a negative 5, I would still get 3.61 times 10 to the negative 6th, but similar to there being two positive charges repelling, two negative charges also repel. So this is very similar to gravitational forces. We can even play around with like moving them towards each other or away from each other, but we're going to kind of skip that step because we did that with gravitational forces. Now what's really interesting is that the forces that we feel, the proportion, the pattern that we observe with gravitational forces is the exact same pattern we observe with electric forces. There's just differences along the way that can kind of trip us up. So first, the differences have to do with what experiences each force. So which experiences gravitational force? Well, we know mass experiences, right, which we use in the units of kilograms. What about what experiences the electric forces? Well, that must be our charges, so we're going to call them protons and electrons. And I wrote P plus and E minus just to kind of identify, right, these are protons and these are electrons. to identify the charge, the positive charge or negative charge. Note, neutrons don't have charge, therefore they don't experience electric force. So which direction is the gravitational force in? Well, hold up something and drop it. No matter what, everything is acting inward. So we're always going to feel an attractive force between two massive, and always attractive. Whereas what we notice in that PhET is when we play around with the positive or negative charges, we notice that we see a both attractive and repelling. Now, since we actually have different attractive or repelling forces that are occurring, we are going to need to decide on a direction, so positive and negative. We haven't done this in the past, and I've been sort of lying to you, but I've been telling you, make sure you focus and you think through which direction the gravitational force is acting in, which is always attractive. And now we're going to have to think through which direction the force is acting in the electric force. But when we start plugging in our variables and our values, we're going to find that an attractive force is negative while a repelling force is positive. And so when we get to the definition of charge, it's really just the difference between, or difference in protons and electrons. And the units are going to be in coulombs. So you might have heard of Coulombic attraction last year in 10th grade chemistry, and this is exactly what we're talking about. And that is a capital C in coulombs. What is the elementary charge? It's the smallest possible charge. That's why it's called elementary. And it's the charge of a proton or an electron. Just one's going to be positive and one's going to be negative. So, and we call it E, with the units of coulombs as well. So let's draw the charges inside these spheres and identify net charges. So I'm going to do positive charges as red charges, and I'm going to do negative charges as blue charges. What we're going to find out is we want to look at the net charge of each of one. So I will draw 1, 2, 3, 4. I'm going to do them all. 1, 2, 3, 4, 5, 6. 1, 2. And 1, 2, 3, 4, 5. I'm going to do negatives. Okay, so negative 2, 3, 4. You might see that I'm spacing them out. That's because protons tend to repel each other, so and electrons will repel each other as well. So they tend to be pretty spaced out. So 1, 2, 3, 4, and 1, 2. I guess 3 and 4, and 7. 1, 2, 3, 4, 5, 6, 7. And when we look at the net charge of these, that's what we have to focus on. We don't want to count how many protons there are. We can't count how many protons or count how many electrons. What we're going to look at is how much is the net charge occurring, which is how much is the charge, the difference between protons and electrons. So I would identify this, and this had 0 E. This would have positive 2 E. This would have negative 2 E. And this would have also negative 2 E. So these are equivalent charges. Even though they have different protons and electrons, they are equivalent. Okay, great. So we know, how much elementary charge more or less there is, 0 E, positive 2 E, negative 2 E, and so forth, but we don't yet know what E is. So in our data booklet, we would find out where it is. This is our base elementary chargers, nothing smaller than that, and you won't find anything with 1.7 times 10 to the negative 19th. 1.6 times 10 to the negative 19th is the um, smallest possible charge, and everything is a multiple of this charge. It's what it's called quantized charges. So if we were to look at a charge of an electron, this is negative 1.6 times 10 to the negative 19th coulombs, where a charge of a proton is positive 1.6 times 10 to the negative 19th coulombs. So since all matter is composed of neutrons, protons, and electrons, the difference between the protons and the electrons will produce only multiples of this elementary charge. So everything has a net charge, which is a multiple of 1.6 times 10 to the negative 19th coulombs. We can see this in our atom, where we have a central nucleus, which are neutrons and protons. Those cannot move. Only the electrons can move. And those electrons can move between elements and create net charges of positive or negative quantities depending on what was moved. And since we're dealing with movement, we need to know mass, because we will need to know mass when we use it in F equals ma equations. So we can calculate an electric force and then determine what acceleration they have. We also have a mass of a proton, because although protons don't move, elements and nuclei can move, which are composed of protons. So let's look at the equations. We've already determined gravitational force equation, right? Newton's law of gravitation. So now we have Coulomb's law, which is the electric force equation. This is in your data booklet, as we showed above. And you might see me write it like this out of my own habit, similar to what I did with gravitational forces. Of course, you choose how you'd like to do it. So K is the new variable, right? We identified what Q and Q are. Those are both charges. But K, we haven't, and that is Coulomb's constant, which has a value of 8.99 times 10 to the 9th newtons meters squared over Coulomb squared. You can think about why those units come up, but they have the same purpose for why the gravitational constant was newtons meters squared over kilograms squared. Right? We needed to cancel out the kilograms in that. In this case, there's no kilograms, there's charge, units of charge. So we need to cancel out the coulombs to get us to newtons. Now, you'll see another equation, which is also in your data booklet. And you might say, wait, this is a constant. So if this is a constant, why is there an equation for it? And why is there this really weird symbol, this epsilon naught? And yeah, that's what I called it. This is, well, I can just write it here, is the unit is a epsilon. I'm sorry, the symbol is an epsilon, and it's written kind of as a puffy E. This case, though, it's epsilon naught, which comes from another constant. Again, kind of annoying, but this constant shows up a lot more in other places as well. And it shows up here where it's called the permittivity of free space. It's a really weird long name. There's also a permeability of free space. This has to do with specifically in a vacuum, the interaction between electric and magnetic fields, but we'll get there later. So all we really need to know is it's a constant in a vacuum. So there is a permittivity of free space in a vacuum, and I'll often just call it the electric constant. So that is what this epsilon naught is. But this only occurs, these constants are only constant. So I'll say only constant in air or a vacuum. That's why we have an equation for it. So there are other values. There might be like other values of water, which then you would have to solve and say, okay, let's find my K of water, my Coulomb's constant, which is 1 over 4 pi epsilon water. So you might have to determine a new Coulombic constant depending on a different epsilon. Those are rare, though. Most of the times we just say, we're dealing with an air in a vacuum, but it can happen. So just note that this equation is in the data booklet for that reason. All right. So going back to what we've seen before, we've identified a electric force equation that uses a Coulomb constant when in air or vacuum. And that force comes from when charges are moving and produce net charges between objects. Or, a net charge is positive or net charge is negative, and there's a difference between these charges. And that can be seen by finding these net charges. So you might see an attraction between, the 2e and the negative 2e, or a repelling force between the two negative 2e's. Those forces are positive or negative, depending on if they're attracting or repelling. And again, it's due to the protons and electrons. So let's go back to kind of our example problem. Before, I solved for a gravitational force, which I remember the gravitational force was something, I think it was times 10 to the negative 47th newtons. And I was like, whoa, that's really, really small. So let's try to calculate the force between the proton and the electron using our electric force equation. We're given the charge, the elementary charge, which we know is going to be equal and opposite for a proton and an electron, and we're given the radius here. So we just need to solve using our equation. Where we have equals 8.99 times 10 to the 9th. Again, we assume that if it doesn't tell us we're in a different medium that has a different electric constant, then we won't need to solve for a new Coulomb constant. I'm going to pause this video and show the work, and then we'll solve it. All right, I got a value of 8.22 times 10 to the power of negative 8 newtons, and specifically a negative. There's two things I want to recognize in this. One, this negative 8 times 10 to the power of negative 8 is significantly larger than times 10 to the negative 47. That means we are times 10 to the 40th stronger of a force. So that shows you the electric force is much, much, much stronger than the gravitational force. Although macroscopically in our lives, it feels like gravity is kind of controlling everything, the electrostatic force or the electric force is really, really, really strong as well. The next thing I want to identify is this negative right here. What does that negative really mean? And that means that it is attractive, because we are looking at a proton and an electron, which means there must be an attractive force going in towards the proton, and it's going to be your electrostatic force. There's nothing different between the electrostatic force and electric force. Those two are the same, so I tend to interchange them. The next question determine, without any calculation, the electric force between two electrons or two protons in this similar situation, in which two electrons or two protons would both equal the same value because they both have the same elementary charge. But since we have a negative times a negative or a positive times a positive, we would end up with a positive 8.22 times 10 to the negative 8 newtons. And that positive here means repelling. So what do negatives and positive forces mean? Kind of re-emphasizing is that positive forces imply repulsion, and attractive forces, negative forces will imply attraction. All right, but now we want to get to fields similar to gravitational fields, where this is just Fg over m. We end up saying that is equal to Gm over r squared. the electric field, which is in your data booklet, is KQ, oh, sorry, I'll start off with FE over Q, which is equal to KQ over R squared. Did I square this one? Yeah, good. And where we look at the definition of a gravitational field, where we focused on it's the force per unit mass acting on a test mass at a specific point in space. Well, this is the force per unit charge acting on a positive test charge at a specific point in space. There's also some value, so per unit charge is important. And then I wrote positive because I wasn't expecting you to get that. But that has to do with whether we end up with a positive electric field value or a negative electric field value. When we canceled out that Q, we don't need it. If we end up with a positive electric field, then that's coming from a proton's electric field because it's pushing it out. Q is going to be positive, and that would be producing a repelling electric field. Whereas if you put a positive charge in the point, it would produce a repulsion. You would have to put a negative charge to change that positive E to a negative value. And then this negative E means there's an attracting electric field. Something to note, like G, technically, this is always negative, because gravitational fields always attract. And so something we kind of like left out, which we can include now, is there's always a negative right here. They don't include it in the data booklet because it shows up more in HL, and they just try to like wash over it. But we will have to include that. That's a negative right there eventually. Now, to be honest, I'm okay in gravitational forces and fields until we get to the HL. Like if you're in SL, just solve for it, know that it's attracting, and we're good. But when we're doing electric forces and fields, we're going to need to know those positives or negatives a lot more because we have positive and negative charges. Now, our last thing I want to talk about is how we identify which force is contributing to any object in orbit. So in this case, a planet is being attracted to the sun. Its net force is inward. It's perpendicular to the direction of motion. The planet is moving at a constant speed. And so there we have a gravitational force is the centripetal force. Now when we go to atoms and charges moving around, we're going to say that the electric force is equal to the centripetal force. And it acts the same way. Again, just M's don't get canceled out because we're dealing with Q's. But that'll show up in the practice. Now, I have a gear up problem, but this it's getting pretty long, so I'm not gonna work on this. But feel free to work on this, and I will post the answers. And see you in class.